Okay, before going into the exact topic of today, let's just remember what we have been studying, what we have studied in the last class. Just a little revision because we were kind of in the middle of the this one, right? The middle of last class, right? The last 5 minutes we didn't get it to revise and everything. So we'll just revise a little bit and then we'll go into the today's topic. Okay. So in the last class we have seen the we have started the topic discussion on the topic of DC generators, and then we have seen what is a generator as well as what is a motor. A generator is a machine which converts the mechanical energy into electrical energy. Here the conversion takes place in the magnetic medium. That is the main concern. Okay. Next is motor. A motor is a machine which converts the electrical energy into mechanical energy. Here also the main medium is the magnetic medium. This also we have seen. Alright. Next, in just to understand the different concepts in this electrical technology, we need to know certain fundamental laws. Those fundamental laws we have seen in the last class. What are the fundamental laws which we have seen? Means basically we have seen Ohm's law, Kirchhoff's law, Faraday's laws of electromagnetic induction, Maxwell's right-hand thumb rule, Lenz's law, um, Fleming's right-hand rule, Fleming's left-hand rule. These are the basic fundamental laws which we have seen. In this, we know what is Ohm's law. V is equals to IR. Ohm's law can be directly defined by the equation V is equals to IR. And we have seen what is this magic triangle and how the V, I and R are related. How is this going? That's what we have seen. Next is Kirchhoff's laws, where it gives us, there are two Kirchhoff's laws. Basically, it gives us the connection between the different currents and different voltages in a closed loop. So, saying that the Kirchhoff's current law is nothing but the law of conservation of charge. That is the current entering into a node is equals to the current exiting a node. That's what is the main Kirchhoff's current law. Then again, we have seen Kirchhoff's voltage law. This is nothing but the conservation of energy. Here, the voltage drops the voltage drops is equals to the voltage rises in a loop. In a closed loop, if you see whatever the voltage rise is there, that will be equal to the voltage drop in the same loop. That is the main Kirchhoff's voltage law. And then we have seen what are Faraday's laws of electromagnetic induction. Basically, Faraday's laws of two basic laws are there: Faraday's first law and Faraday's second law. In the Faraday's first law, he's just telling us that there will be an EMF induced in a conductor when it is moving, when it is changing its direction in the magnetic field. So we have seen different methods in which this can happen. And again, we have seen what is Faraday's second law. This gives us an equation which is nothing but the equation of EMF being that the amount of EMF that is being produced when this happens. Okay, so that is the Faraday's second law. And again, we have seen induced EMF in a straight conductor. Just to understand how the EMF is in a straight conductor, this is an equation: E is equals to BLV sin theta. This also we have seen, and again we have seen Maxwell's right hand thumb rule, which gives us the direction of the magnetic field. So if we are holding a current carrying conductor in our right hand, and the direction of the current is given by the thumb, is indicated by the thumb, then the curl of the fingers gives us the direction of the magnetic field. This also gives us in which direction the magnetic field is being present. And again we have seen Lenz's law. This is like this is similar to what Newton's third law of motion. That means the force, the result will always oppose the source. That is what is the Lenz's law. And again we have Fleming's right hand thumb rule, which gives us the direction of the induced EMF or the current. Induced EMF or the current. We should go for induced EMF because EMF will be induced only if the circuit is closed, then the current will be produced. Okay, so the Fleming's right hand thumb rule, sorry, Fleming's right hand rule gives us the direction of the induced current or induced EMF. So this basically represents this basically will be useful for us when we go for generators. And again, we have Fleming's left hand rule, which gives us the direction of the motion of the conductor. So this will help us in understanding the motion of the motor. Okay, in the operation of the motor, where the mechanical energy is the output, here Fleming's left hand rule will be useful. Now coming to our topic, that is the DC generators. First thing which we need to understand is the principle of operation of a DC generator. So let us see what is the principle of operation of a DC generator. So here on your slide, in this slide you can see that any electrical generator is based on the principle that whenever flux is cut by a conductor, whenever a flux is cut by a conductor, an EMF is induced which will cause a current to flow in the conductor if the conductor circuit is closed. This concept is nothing but the dynamically induced EMF concept. Dynamically induced EMF concept. So, the principle of operation of a DC generator is dynamically induced EMF, and the direction of this induced EMF and also whatever the current, whatever the resulting current might be, that will be given by the Fleming's right hand rule. Fleming's right hand rule. Okay, so the principle of operation for the DC generator is dynamically induced EMF, and the direction is given by the Fleming's right hand rule. So, if you just look at this definition and look at this thing, you can understand that there are some basic components which are required for a generator to operate. So, basically, what are those essential components which generator requires means? The first thing is a magnetic field. We need to create a magnetic field because in that magnetic field only, if the current carrying conductor is placed or if a conductor is placed and the relative magnetic field of the conductor is being changed, only then the EMF is induced, right? That is the Faraday's laws of electromagnetic induction. So, basic thing is we need a magnetic field, and again we need a conductor, right? We need a conductor so that we can change the magnetic field of the conductor and then an EMF will be produced in the conductor. So, we need a conductor, or we need a bunch of conductors. We need a bunch of conductors. If we have only one conductor, some EMF will be generated. But if we have a bunch of conductors, then a lot of EMF can be generated. So we need a conductor or a group of conductors or a bunch of conductors. Okay. The third one is motion of the conductor with respect to the magnetic field. Right. So we need to if we just have a magnetic field and we have a conductor, that doesn't induce any EMF into the conductor, right? So first we need to have a magnetic field as well as we need to have a conductor, and this conductor should move in the magnetic field. Should move in the magnetic field, or at least the magnetic field should move relative to the conductor. So basically we need to have a conductor and a motion of the conductor with respect to the magnetic field. We need to have a motion of the conductor with respect to the magnetic field. So these are the main components for a generator to be operating. Okay, so basically we need a magnetic field, we need a conductor or a group of conductors, and we need a motion of the conductor with respect to the magnetic field. We need to have a relative motion of the conductor with respect to the magnetic field. So here he is giving us just an overview of a generator, how it works and what are the different parts, how these parts are being working together. Here you can see this golden color thing which is rotating is nothing but a conductor. Here you can see N and S. These are nothing but the magnetic field, and we are rotating this conductor. So we have conductors, we have magnetic field, as well as this conductor is being rotated. So this gives us a general idea of how a generator should be. Okay. Now, in order to understand the total concept of generation, the total concept of power generation and everything, we are going to take a simple loop generator. What does the simple loop generator, what does the simple loop generator comprise of means? It just is a loop like this. Okay, it has a conductor which is being connected at both ends. Here you can see it. here here whatever you are seeing, this AB part, this is a conductor, and this CD part is a conductor, and these two conductors are connected. That's all. This is just the connection. Okay, and then we have two conductors that are being connected into a loop. Okay, here whatever, here we have an external load. Let us say we will be having some load. Okay, I'll just connect the load like this. Cool. So we have a load and we are connecting the load to the generator. Okay. So this is a structure of a simple loop generator. So uh, okay, he's giving us how this simple loop generator is. Consider a single turn loop ABCD rotating clockwise in a uniform magnetic field with a constant speed, as shown in figure 1.1. So here is the figure. So he is saying that we have we have a simple loop conductor which is labeled as ABCD. ABCD, and this conductor is being moved in a magnetic field. This conductor is being moved in a magnetic field. And what is the direction of the motion of the conductor? Means it is a clockwise motion. We are rotating the conductor in a clockwise direction. Okay. As the loop rotates, the flux linking the coil sides A, B and C, D changes continuously. Right. Now you are rotating the conductor in a magnetic field. That means continuously whatever the magnetic field of the conductor is there, that is being changed. Right. Because you are moving the conductor in a magnetic field, and that conductor which is being moved in the magnetic field experiences different amount of magnetic field at different points of time, right? So every single point of time the conductors will be experiencing different amount of magnetic field. That means the magnetic field of that particular conductor is being disrupted continuously. That means the magnetic field of that particular conductor is being disrupted continuously, so that there will be an EMF produced in that particular conductor. Okay. So let us see. Hence, the EMF induced in this coil sides also changes, but the EMF induced in one coil side aids to that induced in the other coil. So he is saying that there will be an induced EMF in these coils, and these will be just a second. Okay. And this induced EMFs, how they will be means, these induced EMFs will be aiding each other. He's saying that these induced EMFs will be aiding each other. Let us see whether that is true or not. Okay. Now, let us take this AB conductor, that is AB side of this conductor. Now, I am just considering this conductor side, that is AB side of the conductor. Now, by using the Fleming's right hand rule, can you just understand what? Can you just give us any direction in which the EMF can be produced? If you just, we know what is Fleming's right hand rule, right? Fleming's right hand rule tells us if the forefinger represents the direction of the field, and then uh, thumb represents the direction of the motion, that is like this, right? Field and also motion. Okay, this conductor is being moving upwards, so I'm keeping my finger upwards, and then we know that the direction is not from north to south. Now someone has their mic on, please make sure it is muted. Oh, so now he's saying that we are having north to south, right? And again, we are showing the direction of the motion of the conductor. And now I can say that the direction of the induced EMF will be given by the what do you say, central finger, right? So I'm just putting like this. So that means the direction of the EMF will be from B to A, from B to A. Now, in the similar manner, just understand how the direction of the EMF will be in C to D. Now, if you see, for C to D also, the EMF induced will be in this direction. But the motion of the conductor is in the opposite direction, right? So, like this. Okay. I can't show you physically, but, but just try and understand it. It is in the opposite direction, right? So, again, okay, like this. So, I can't show you guys. Right. So EMF, the motion of the conductor is in the opposite direction, and then the EMF is the magnetic field is in north-south direction. Now the induced EMF will be towards me, right? Will be towards me. That is, this will be the direction of the induced EMF from that is from B to C. From B to A will be the direction of induced EMF in the conductor AB, and from in the conductor DC the direction of the induced EMF is from D to C. So you as you can see, this concludes this loop. This is showing us a total loop, right? You can see that the current, if this circuit is being closed, if this circuit, let us say this circuit is closed, now the direction of the current will be from B to A, and then it passes through this conductor, and then it will come from D to C. That means the total current is flowing in this direction. The total current is flowing in this. That is the conductor, the whatever the induced EMF is there in each of the conductors, that is being aided by each other. That is being aided by each other. That is the statement which is given here. That is, sorry. Hence, the EMF induced in these coils also changes, but the EMF induced in one coil adds to the induced induced in the other coil. So he's saying that both of the EMFs, whatever we have, those are in aiding position. So we have seen how this aiding position is being obtained. So let us see what are the different positions of this conductor and how the different EMFs can be generated. Let us see. When the loop is in the position 1, that is in the figure 1.1, let us see what is position 1. So he is saying this is position 1. Position 1, here also you can see the position 1. That is exactly opposite to the EMF. Exactly opposite to the EMF. That is, because this is a single loop generator, we have a wire and we have EMF, and we have the magnetic field, and the magnetic field is the wire is not cutting the magnetic field. The wire is not at all cutting the magnetic field. That means there is no change in the magnetic field of the conductor. There is no change in the magnetic field of the conductor. So what will be the amount of induced EMF? The amount of induced EMF will be 0. The amount of induced EMF will be 0. Now, let us see what happens if we just move the conductor slightly. If we are just moving the conductor a little bit, that is position 2. In this position 2, some of the lines of flux are being cut by the conductor. Some of the lines of flux are being cut by the conductor. So, a little amount of EMF will be generated. So, a little amount of EMF will be generated. First thing is, when the conductor is in position 1, no EMF is being generated because there is no change in the flux linkages. There is no change in the magnetic field of the conductors. So, that is why here we are showing 0. That is, in this right side you are seeing a graph which is showing us the EMF versus angle at which this conductor is being cut. Okay, so here you can see that EMF at position 1 is 0. In the similar manner, if the position is being changed slightly, then there will be some EMF that is being generated, that is being shown here by the position 2. Now, let us say in the third position, that is totally opposite to the EMF. Now, if the conductor is like this and the magnetic field is like this, now the total conductor is cutting this magnetic field. The total conductor is cutting this magnetic field. That means there will be a large amount of EMF that will be generated in the conductor. That is the maximum amount of EMF that is being in induced in the conductor is when the conductor is in the position 3. So here we are showing the position 3. In the similar way, now the conductor is moving towards downside. So now again the area which the conductor is being exposed is reducing, and again when it comes to exactly 90 degrees, like 180 degrees, there will be again no cutting of the flux, and then the sorry, there will be no cutting of the flux, and then there will be no EMF that is being induced. So this is the first cycle, that is from first position to fifth position. From the first position to fifth position, here you can see it. From the first position to fifth position, the EMF is slowly increasing, reaches maximum, slowly decreasing, and then reaches zero again. So this is the first cycle. So this part gives us this part gives us how the EMF is being generated in the positions from 1 to 5. Again, here after position 5, what happens is the conductor is being moved like this, right? Again, it is coming back to its original position. So, but the thing is, while it is coming back to its original position, because of the change in the direction of motion, the direction of EMF that is being induced into the conductors will also be changed. The direction of EMF that is being induced in the conductor will also be changed. You just use the Fleming's right hand rule and then try to determine the direction of the EMF induced. In the previous case, we had the EMF that is being induced from in the direction of BA and DC, right? BA and DC. Now, because of the change in the direction of motion, it will be from AB to CD. AB to CD. Okay. So because of this change, here also you can see that the EMF direction will also be changed. Okay. So similar way, now again the amount of flux that is being cut in the position 6 is a little less. So there will be a less amount of EMF that is being produced. Again, in the position 7, maximum amount of friction is there, that is maximum amount of flux is being cut, so there will be maximum amount of EMF that is being produced. And again in position 8, again only some is there, so we will get a little amount of voltage, and then it is returning to position 1 where there is no EMF that is being produced. So in this way the simple loop generator produces EMF. Okay, in this way the simple loop generator produces EMF. So that is what is saying. Now we need to understand that EMF generated in the loop, that is the EMF that is being generated here, is an alternating one. Yes, right. So here you can see there is a positive cycle. There is a positive cycle here. This is the positive one, and then we have a negative one also, right? We have a negative cycle also. That is the EMF value which is being produced in this particular single loop generator. Is an alternating one. It is an alternating current that is being produced. Okay. So, but this is a DC generator and we are producing AC. How to convert this produced AC into DC means we are going to use a device called as commutator, which will convert the AC voltage that is being generated into DC voltage. We are going to use a small device called as commutator, which will be converting the alternating voltage that is being generated into a direct voltage that is being generated. Basically, first thing we need to understand is why are we getting this alternating voltage? Why are we getting this alternating voltage? Why the voltage is increasing at a point of time, and then because of the change of the direction in the motion of the conductor, then the what do you say, the direction of the induced EMF is changing. Why is this happening? First we need to understand. Here if you see this conductor which is AB, the conductor which is AB, in the first part of our conversation, that is when we are talking about positions 1 to 5, the conductor AB is under the influence of north pole. Sorry, it is in the influence of the south pole, and the conductor DC is in the influence of the north pole, right? So if you just look at this diagram, here you can say that from the positions 1 to 5, the conductor AB is under the influence of the south pole, whereas the conductor DC is under the influence of the north pole. From the position 6 through 1, again that the cycle, there the conductor is, the influence of the conductor is changed. The influence in which the conductor is present is changed. That the magnetic field from the positions 6 to 1, the conductor AB is under the influence of the north pole, whereas the conductor CD is in the influence of the south pole. That is, the influence is being changed. The magnetic field in which the conductor is present is changed because of the position, because of the changing position of the conductor. Because of this changing nature of the field, we are having this alternating type of current. But if we can somehow manage that AB is always under the influence of north pole and CD is always under the influence of south pole, or vice versa, however it might be, if we can maintain in such a way that the conductor is always under the influence of the same pole, then then this current which is alternating will become a direct current. That means it will be producing a constant, only half of the peaks, that is either the upper half of the peak or this lower half of the peak. That is, if we can manage, if we can manage that AB is always under south pole, that means AB is always under south pole means this will get repeated, right? AB will be always producing same type of current, that is unidirectional current, unidirectional EMF. That is, you will get a DC EMF. So in order to make sure that this is happening, in order to make sure that this conductor is always under the same influence, we can go for a different type of construction of the generator, which is called as homopolar generator. That means always this AB will be under the similar pole, that is homopole, only single type of pole. But that homopolar construction is a little difficult one. That homopolar construction is a little difficult one. So what we are going to do instead of going for this homopolar construction means, in this heteropolar construction itself, we are going to introduce a small device which is called as a commutator, which makes sure that always the current collected by one of the rings is, the current collected is in unidirection. Let us see how this is happening. So, if somehow the connection of the coil side to the external load is reversed, at the same instant the current in the coil side reverses, the current through the load will be a direct current, right? So, if we can just make sure that the direction of current in the load, the direction of the current in the circuit doesn't change, that is, you need to make sure that if the direction of the current is changing, at the same time if the coil side also, direction of the coil side also changes, then we can make sure that there will be a direct current that is being produced in this particular machine, right? How can we do this? Means we can do this with what is called as a commutator, okay? So let us see how the commutator is being designed. The commutator is a cylindrical device which contains two sections, that is C1 and C2 sections. So these two sections are being separated by a thin sheet of an insulator such as mica. Okay, the thin sheet of insulator is being present between these two parts, that is C1 and C2, and that mica will allow us will not allow the current to pass through from one side to another side. Okay, so it consists of it consists of a cylindrical metal ring cut into two halves or segments C1 and C2 respectively, separated by a thin sheet of mica. The commutator is mounted on but insulated from the rotor shaft. So what we are going to do is, we are going to keep this commutator in the onto the conductors, but this rotor, whatever the rotor shaft is there, that shaft will be different. We should make sure that shaft is not touching the commutator. Okay, now the ends of the coils AB and CD are connected to the segments C1 and C2 respectively. That's what he's saying. So AB, the conductor AB will be connected to C1, and then the conductor CD will be connected to C2. That is what he's saying. Okay. Now, two stationary carbon brushes rest on the commutator and lead the current to the external circuit. These small squares which you are seeing are nothing but the brushes. I'll just show you. This is the brush, this one and this one. These two are the brushes. These are made of carbon, so these are called as carbon brushes. These two brushes are present, and these two brushes will collect the current from the circuit and lead it to an external device. With this arrangement, the commutator at all times connects the coil side under south pole to positive brush and that under north pole to negative brush. So here if you can see, now this C1 and C2 are rotating along with AB and CD. Along with AB and CD, this C1 and C2 are rotating, but C1 is making sure C1 and C2, these two are making sure that whatever the coil might be under the south pole influence, that coil is connected to the positive brush. That coil is being connected to the positive brush. In a similar manner, whatever the coil that might be under the north pole, under the influence of the north pole, that is being connected to the negative brush. How is this possible? You can see here right away. So here in the first position, see under C1, the C1 is connected to AB, and under north pole AB is there, and under south pole DC is there. So C1 is connected to the negative brush and C2 is connected to the positive brush. And now the the generator is being turned again. Now here you can see that again in the CD, whatever is there in the north pole influence, that is being connected to the negative brush, that is north pole negative brush, south pole positive brush. That's all. So either it might be AB or CD, that this commutator is making sure that whatever it might be, whether it might be AB or CD, always whatever is under north pole, that is being connected to the negative pole. Whatever is under the south pole, that is being connected to the positive pole, such that here, because of this continuous change, continuously making sure that whatever is in the north pole influence, that is being connected to the negative pole, and south pole influence, that is being connected to the positive brush. Now because of this, the direction of current outside the circuit, that is in this resistor R, the direction of the current will always be constant. The direction of the current will always be constant. This total thing is accomplished by this commutator. In figure 1.4, the coil sets AB and CD are under north pole and south pole respectively. Note that the segment C1 connects the coil side AB to the point P of the load resistance R, and segment C2 connects the coil side CD to the point Q of the load. Also note the direction of the current through the load, that is from Q to P. Okay. Now after half a revolution sorry. After half revolution of the loop, that is at a 180 degrees rotation, the coil side AB is under south pole and the coil side CD is under the north pole as shown in the figure. The currents in the coil sides now flow moved through 180 degrees, flow in the reverse direction, but the segment C1 and C2 have also moved through 180 degrees. That is, segment C1 is now connected with the positive. That is whatever it might be. At the end of the discussion, we are making sure that the direction of current through R is constant. Okay, through R is constant. So this is the role of the commutator. This is the role of the commutator. Thus, the alternating voltage generated in the loop will appear as the direct voltage at the brushes. So, if you just look at how the direction of the current is at the brushes, it is always constant. So, whatever might be the current that is being produced in the loop, we are making sure that whatever the current that we are carrying out of the loop is always unidirectional, that is direct current. Okay, it is to be noted that the EMF generated in the armature winding of a DC generator is an alternating one. We know this, right? It is by the use of the commutator that we are converting the generated alternating EMF into direct voltage. Okay, so you need to make sure, we need to understand this one, that the EMF generated in the armature winding is always an alternating one, but because of the use of the commutator, we are changing the alternating EMF that is being produced into direct voltage. Okay, the purpose of the brushes is simply to lead the current from the rotating loop or winding to the external stationary loop. That's all. The only thing the brushes does is it just collects the current from the conductors and then give it to the load. Okay, it just collects the current from the conductors and then give it to the load. The variation of the voltage across the brushes with the angular displacement of the loop is shown in the figure 1.6. Here is showing how the variation of the current is there along with respect to the brushes, how the brushes experience the variation of the voltage. Okay. Now, this is not a steady direct voltage but has pulsating character, right? This is not a pure DC voltage. It is having a little pulsations, right? It is moving, it is having pulsations. Okay. It is because the voltage appearing across the brush varies from 0 to maximum value and back to 0 twice for each of the revolution of the loop, right? So, 2 times the value of the current goes from 0 to maximum and again from maximum to 0, again 0 to maximum, maximum to 0. Because of this nature, the direct current which we are getting in this direction, in this way, is a pulsating one. A pulsating direct voltage such as is produced where single loop is not suitable for many commercial uses. Because the voltage is being varied throughout the total cycle, what happens is the amount of voltage which we are getting is very pulsating and this cannot be used for commercial usages. What we require is a steady state direct voltage. Okay, we need a steady voltage. This can be achieved by using a large number of coils connected in series. So if we are just connecting, instead of taking a single loop, if we have multiple loops, then there will be multiple amounts of voltages that are being generated, and that can make sure that whatever we are getting is a smooth direct voltage. That can make sure that whatever we are getting as the output as a smooth voltage. So this results in an arrangement known as the armature winding. So because we are going for multiple loops, we are going for many number of coils, then that type of arrangement is called as an armature winding. Okay, so we'll see what is an armature winding and how this is being, what are the different structures and everything. Okay, here you can see a simple animation which gives us a simple arrangement. So if we do not have any commutator, then the current that is being produced will be of alternating nature. That means we'll have a positive cycle as well as we have a negative cycle. But if we have a commutator, the direction of the current, the direction of the voltage can be made sure it is in a unidirectional way. That is, we are getting a direct current. So this animation gives us a simple example of that particular topic. Okay, so this is the so let's end the class here. Okay, for today's topic, this is the end of the class. We'll see what is an armature winding and what are the construction features of the DC generator in the upcoming class.